Hi, my name is Diksha Tiwari and this is my first solution presentation for APS 163, and the problem has been added in the description below and has been taken from chapter 8 of the Briggs textbook. And the problem here deals with initial value problems. Given an initial set of conditions, we're going to try and model the behavior of the system in the future. So in the question, we've been given a pond and we can try and model this as a tank to try and come up with a differential equation. And so we can start off with a diagram. So we know that at time is equal to 0, this tank had 10 raised to 6 liters of pure water in it when concentration of 20 grams per liter of pollutants were added to it. And so if we multiply that by the volume, we can get the mass of the pollutants that was there in the pond at time is equal to 0. So these are our initial conditions for the initial value problem, which we will be then utilizing later. Now, we are also given that the volume entering the volume of pure water entering the tank, entering the pond, and the volume of water that is exiting the tank, or the rates at which this is happening, are equal to 1,200 liters per hour in both cases. So this is the rate at which the water is exiting and the rate at which the water is entering the tank, the pond. Now, in order to try and get an equation for the way the mass is changing within the pond, the mass of the pollutants inside the ponds are changing, we can find that using the rates at which the mass of at which the pollutants are entering the tank and leaving the tank in terms of its mass. So in order to do that, we can write this equation where this is the rate at which pollutants are entering the tank and this is the rate at which the pollutants are exiting the tank in kg per hour. So in order to do this, we can find the concentration of the pollutants entering the tank times the volume minus the concentration exiting the tank times the volume that's exiting. Now, this we can tell because from the question we've been given that there is only pure water entering the pond. This is going to be 0, and this volume is going to remain 1,200 liters per hour. This, we don't know the exact concentration that's coming out of the pond. However, we do know that it's going to be related to the mass of the pollutants that's there inside the pond. And so we can generalize that with MT. And that's also going to be dependent on the volume of the pond at that particular point in time. And so we take that as VT. And we multiply that by 1,200. We can try and find VT using the same logic that we tried to use for MT, by calculating the rate at which the volume is entering the tank and the volume at which it is exiting. And so we get 0. Now integrating both sides, we get this, and this is where we would use the first initial value function that we have. So we could probably write this somewhere on the top. On integrating Vt, we get 0t plus c, and V naught is equal to 10 raised to 6 liters, and so c is equal to 10 raised to 6. And so we know that the volume of the tank is not changing with respect to time. It remains the same. And now we can plug that back into our equation for MT, which says 0 minus 1,200 times MT, 10 raised to 6. And so we get a simple separable first order differential equation that we can now integrate and so we get ln of m is equal to minus 12 over 10 raised to 4t plus some arbitrary constant c dash. Now in order to find c dash, again we can use our initial value and get m0 is equal to e raised to minus 12, 10 raised to 40 plus c dash. E raised to c dash is equal to 20 times 10 raised to 6, which we can call some arbitrary constant k. And so our equation for mt then becomes k times e raised to minus 12 over 10 raised to 4t, where k is that. And this makes sense because we would expect the number of pollutants to start tending to zero as time goes on, because only pure water is entering the tank and there are no pollutants that are entering the tank. There's only pure water, and so this absolutely makes sense. And when time is equal to 0, we have the 20 times 10 raised to 6 as the mass of the pollutants that's there in the tank at that point in time. And now we can try and solve for the very last part of this question. It is asking us how long it would take to reduce the concentration of the solution in the pond to 10% of its initial value. And so we want the time when c at a certain time t is going to be equal to c of where ct over c of 0 is going to be equal to 0.1 or 10%. Now ct can be written as mt times vt over c naught times m naught times v naught is equal to 0.1. But we know that vt and v naught are essentially the same value because vt did not change. It was 10 raised to 6 liters because the volume coming in and the volume going out are exactly the same, and so we can cancel these two. And so we get mt over m naught is equal to 0.1. And so 20 times 10 raised to 6 times e raised to minus 12 over 10 raised to 4t over 20 into 10 raised to 6 is equal to 0.1. These cancel out, and so writing this out neatly once again, we get e raised to minus 12 over 10 raised to 4t is equal to 0.1. Taking ln on both sides, we get ln 0.1, and so t is going to be equal to, plugging it into a calculator, we get 1918.82 hours, which is roughly 80 days. And so it would take 80 days for the pollutants to become 10% of its initial value. And that's how you'd solve this problem.